Take any
All right,
questions.
so I am gonna be presenting my role in a project that has been led by Jessica Liu at UC Berkeley, along with some other collaborators. This has been a long-term project working with Keck that I've just been involved with over the past couple of years. So our science goal with this program is to study the population of black holes in the Milky Way and study their distribution of masses and kinematics in order to constrain the evolution processes of high mass stars, as well as supernova physics. So if we look at the population of known black holes in the Milky Way today, the vast majority of these objects come from X-ray binaries, where we can detect black holes through their accretion of matter from a luminous companion star. There are also a number of detached binaries where we've detected black holes through the radial velocity or astrometric motion of a luminous companion. And then we've got one single black hole on this chart that is isolated. And so we are interested in using gravitational microlensing to find these isolated stellar mass black holes because we think the majority of black holes, they form from these really violent processes, are probably going to be isolated and not have held on to any companions. But these objects are really hard to find. So we use gravitational microlensing to find these objects despite them not being luminous. Yep. Okay, well, I think I'll keep talking anyway. My animation doesn't work. I tried it during the lunch break. But we had the great fish video earlier, so you all get gravitational lenses. But I have just like a still from a couple stills from my animation here to show the important points. So just to talk about the scale of gravitational lensing that we mean in microlensing. This is an example kind of snapshot in the middle of a microlensing event where you've got a luminous background star with these two warped images around a black hole that is lensing it. So microlensing, the micro part means that we're working on a scale where we can't actually resolve these separate images. And in addition, these events are transient and changing with time because we're looking at a star and a black hole that are in the Milky Way that have relative proper motions to each other. So the separation of these two images is going to be on the physical scale of like milliarc seconds. We're not going to resolve that. But what we can observe in these microlensing events is an apparent change in the source's brightness over time, as well as a small apparent shift in the star's centroid position. So this is just an example of what those signals can look like. So we've got a photometric signal that occurs kind of first on a relatively short time scale. For a black hole, this will be a few months. For a star, it can be, weeks to a month. And then there's the astrometric shift, which fortunately for us peaks after the photometric peak of the event. So we can look at all of the photometric microlensing events that come out of these ground-based photometric surveys that don't have super high spatial resolution, but they produce a couple thousand alerts a year of ongoing microlensing events. And then we can go through those, select the most interesting ones to follow up with astrometry. So we need to use instruments like Keck with adaptive optics, HST, or JWST for diffraction limited imaging, because we're trying to detect astrometric shifts that are on the order of a milliarc second if we're lucky, sometimes even smaller. And in addition, the astrometric signal of these events evolves a lot more slowly with time than the photometric signal. So we need to monitor these events over the course of several years to catch that deviation of the astrometric trajectory, as well as measure the baseline proper motion of the source star so that we can recognize that that trajectory was in fact a deviation. So there's a couple of things that we look at in these photometric surveys to try to pick the most interesting candidates for potential black holes. So these are two parameters that come out of a light curve, just the time scale of the event and the microlensing parallax. So that's a quantity that basically just says how strongly does Earth's motion around the sun, that parallax signal, affect the shape of your light curve. And so a long time scale and a low microlensing parallax can hint that you might have a high mass lens. So that means you might be looking at a black hole instead of an average star that's going to be of a significantly lower mass. But from that photometric signal alone, all we can measure is a degenerate function of mass and distance. So if we actually want to get a true measurement of the mass, we need to make this astrometric measurement and actually detect that deviation. Once we've done that, if we have a mass measurement, and let's say we see that an object is 3 solar masses or higher, and we have our observed limits on the brightness, and we're not seeing a bright booming O or B star there, then we know that we must have had a black hole lens. So this has been done successfully one time so far. We have one isolated stellar mass black hole that we know of. And this was some great work that came out of Berkeley before I started working there from Casey Lamb and Jessica Liu. And this was performed with HST follow-up of ground-based detection. And so it's really exciting that this first discovery has happened, but we're going to need more of them and to build up a population so that we can actually draw conclusions about the mass function and the distribution of kicks that these black holes get in their formation process. So we are using Keck to try to do this with the NERC-2 and OSIRIS instruments. We use laser guide star imaging because these aren't particularly bright targets, and we need to get the best astrometric precision that we can. So the data analysis I've been working on is primarily NERC-2 data, but the team switched over to using OSIRIS in spring of 2019 because it has a large field of view, and that allows us to get some more reference stars to better characterize the reference frame for our astrometric positions. And so Jessica Liu and collaborators demonstrated in their 2016 paper that you can achieve about 0.15 milliarcsecond astrometric precision for bright stars using this Keck observing scheme, which is about what we need in order to be able to detect the astrometric shifts of black holes. So after we've collected our data from Keck, we use the KAI pipeline, the Keck Adaptive Optics Imaging Data Reduction Pipeline. I won't really get into that, but I'll just say go see Natasha Abrams' poster to hear more about this during the break. I had to struggle through using the IRAF version of the code with the one computer that our group has that can still run IRAF that I have to go reboot anytime I want to use it. So definitely check out Natasha's work so you don't have to do what I did. And then after we've finally fought with that computer to get our data out, I run it through the FlyStar astrometric alignment code. So what we're measuring really is the relative astrometry between our target star and reference stars in the field, because we don't have absolute astrometry down to the milliarcsecond level. So this is a code called FlyStar that we run, where we start with a catalog of stars from each of our observation epochs with stars with their positions and magnitudes. So FlyStar will match these star lists to each other and fit them with transformations to account for any small distortions that remain in those images. And then we have each star's transformed position over time, and we can fit that to a model of stellar motion, so proper motion across the sky. And then we kind of continue this loop of matching, transforming, refining our stellar motion model fits until we're happy with our output. And then we've got our final output of the star's transformed positions and motion model parameters. Something that I did a lot of work on recently was updating the FlyStar code to be able to model parallax, because we were actually seeing parallax in the residuals of a few of our bright stars in a couple of our microlensing events. So we can now actually subtract that out in our astrometric alignment as well. So after this, this is a long data analysis process. We'll then run joint photometry and astrometry fits on our targets in order to set an upper limit on the mass of the lens, or to measure the lens mass. And so I'm on limited time today, so I'll just kind of quickly summarize my results. I have been running reanalysis on a few targets that peaked in 2012 to 2015. So we've got several years of follow-up on these candidates. And unfortunately, I am not able to report a new black hole detection for you today. I have 2 events where we have upper mass limits that rule out a black hole lens. I've got 1 event where unfortunately we had a few rough nights and we're not even able to put an upper mass limit on it to rule out a black hole. I do have 1 very interesting event where we're seeing some sort of astrometric deviation in the signal, but our microlensing fitting code provides both a neutron star solution and a low mass star solution. So We ended up proposing and getting time for another Keck observation of this target in August of 2025. And I was really hoping to slide that in the alignment and have an exciting result for you all today. But unfortunately, there are some weird residuals going on in that result. So I think what we need to do here is get an updated distortion solution for OSIRIS into the chi reduction pipeline and try reanalyzing that data again. There's some great work going on at UC Berkeley, led by Charles Antoine Claveau, to work on this. So they're going to get that into the chi pipeline soon, and hopefully I'll have a cool result to publish soon on that target. So I'll just kind of breeze through the last few things here, but I wanted to mention some other things that we're doing with Keck now is using Keck to fill in the gaps in space-based observations of interesting microlensing targets. So we're doing this already to observe some of our targets in the fall, where HST can no longer observe a galactic bulge that time of year due to reduced gyro mode. So Keck has been really instrumental in allowing us to continue monitoring some of our HST events. And we've also got a lot of plans to do a similar thing with Roman once it comes online in the next couple of years. And so kind of just the last thing I wanted to mention real quick here is I wanted to give a big thank you to the whole Keck operations and AO team, because I know they've been working really hard in the last year and longer to improve the performance of the OSIRIS adaptive optics system. And so a short version of this plot here is I've got a bunch of points in red towards that that worst quality part of the plot, and then a bunch of our new points from 2025 in black towards that better quality part of the plot. So we've seen a dramatic improvement in the performance of Keck AO this past year that we're really excited to get even better constraints on the targets that we're currently monitoring. So I'll leave up my summary.
Awesome.